Welcome back. This is tutorial 10, hypothesis testing 2. Finally, we're going to talk about p-values in this tutorial, and we use it a lot, and particularly for people doing another course that comes after this one, ECON1310. We'll be looking at both confidence intervals, p-values, and t-statistics a lot, and how they communicate to each other. Right? How all of the three give the same information in the end. But before we start with that, let's go to some admin stuff. LBRT is open, as you might know. LBRT 2, the second attempt. So, as I've been saying before, most of the people doing a second attempt end up increasing their grades. So, and we only consider the highest one. So I strongly recommend, although I noticed that for the first attempt, a lot of the people did quite well. Almost nobody got the maximum score. So there's always some extra opportunity to increase your grades. And it's also extra training. Maybe during the second attempt might help you with the LBRT 3, perhaps, because we're still using the same equations, although a few things change. It's the same idea, same equations, same distributions. So even if you're very happy with your LBRT 2 first attempt, great. I would suggest doing the second one. It will be open until 4 p.m. Brisbane time tomorrow, Friday. So you still have today to the end of the day, plus tomorrow until 4 p.m. Using Brisbane time. And it's the same as per usual. You guys, most of you did the first attempt. So I'm sure you do super well in the second attempt too. And hopefully increase your grades as it usually happens. All right. And other than LBRT 2, let's see, in preparation, familiarize. Other than that, we also have CML 4 and 5. The second attempt of CML 4 ends tomorrow at 4 p.m., while the first attempt of CML 5, you have until Monday. So you still have the weekend to work on that. Therefore, if you have to choose things or put things in order, definitely LBRT 2 second attempt priority, because it's worth 20%. CML 4 second attempt after that, because it's until Friday, and then maybe for the weekend or just after this, guys, first attempt of CML 5. Okay, good luck with all of this, and I think we can, unless you have any question, let me open the chat. We can go ahead with our tutorial. Today is the second, this one is the second tutorial of hypothesis testing. And we'll be looking at pretty much the same things that we were looking at last tutorial. But now we're checking this p-value that we will be using for the first time. And it's important, this tutorial is important to show you that it's not, and basically it's not anything new. It was always there, but we were just not looking at it. And we will see how this p-value is a little bit of the area of our distribution and how we calculate it. Okay. And then we have carry out one-tail and two-tail hypothesis, test for p-value, for population proportions, and carry out a hypothesis test for the difference between two means using the pool variance method. It will be a longer exercise, and we'll take the second half of this tutorial during that one. So that's it. We'll have 2 questions for the first half and this last one for the last one. All right. Let's go. Question 1. And as probably you expect already, let's see, there is a poll for us to find the symbols we're going to use in each of these values, right? So GEI developed a new bulb. Bulb is the bulb where the light comes from. whose design specifications call for a mean light output of 960 lumens. Lumens is just a unit of measure of amount of light, compared to an earlier model that provided only 750 lumens. The company's data indicate that the standard deviation of light output for this type of bulb is 18.4 lumens, and light output is approximately normally distributed. From a sample of 20 new bulbs, the testing committee found an average light output of 954 lumens per bulb, and a 0.05 significance level. Can GEI conclude that its new bulb is producing the specified mean 960 lumen output? Use p-value approach. Use the p-value approach. So I have 3 answers up to now. It's 5 questions. I understand if it's a little bit more challenging at first. It's normal. I'll give you another 30 seconds, 6 answers up to now. So we're looking for 90 lumens. What is it talking about? Which symbol for it? One. Then 18.4 lumens, which is here. The company's data indicate that the standard deviation of light output for this type of bulb is 18.4. Then we're looking for what are the 20 new bulbs that is here, and the 954 lumens that is there, the same phrase. Finally, the 0.05 significance level. I have 12 answers out of 21, and I'm going to close the poll in 5 seconds. All right, 3, 2, 1. Amazing. 14 answers. I'll share with you, and let's have a look at the answers. So let's start here. 960 is what we're testing against, and it's definitely not the output of our sample. The output of our sample is this 500 and 954, right? So 960 is a mu. It's a population. I forgot to highlight it down here, but it's the population mu. Then 18.4 is also a standard deviation for the population, because it says the company's data indicate that the standard deviation. So it's something from the past. It's not an output of our sample. All right. Then after this, 20 new bulbs is the size of our sample. 954, it's the X bar because it's coming from the sample. And finally, alpha is 0.05. There. Let's look. So for the mu, 6 out of 14 got it right. For the sigma, 9 out of 13 got it right. Very good job. For n, like 10 out of 14. For X bar, 8 out of 14. And finally, alpha, 9 out of 14. Good job, guys. Very good. Stop sharing because there is more. Now will be a type of problem. So once again, I'm giving you some advice of the things we found already, so you can make a choice of what type of problem we have. Look, I've added the salmon versus trout here. And this, I was going to say, this changes the fact I used to tell you that the t-table only goes with the shag. And for the first time, now that we have the salmon versus trout, the t-table goes also with the salmon versus trout. I'm not saying that this exercise is a salmon versus trout, just mentioning that this is something new. So both of this would be t, and the other 3 would be z, okay? The value of alpha, and what type of test is it, right? Is it talking about increasing or being greater or decreasing or being smaller? Or is it not talking about anything or talking about both ways? Or I have 10 answers, another 15 seconds, 11, because this one is not too much and you have most. Look. I think I had an issue with my monitor. It went blank. Can you guys still see things? It says it's still sharing. Sorry for that. So my monitor ended. The poll ended with 14. No. Wait. Sorry for that, guys. Can I please have a confirmation that you guys can still see my screen or anything? Perfect. Yes, thank you so much. Yeah, I do know why my monitor went dark and came back, and a few things are a little bit different. I will end the poll. I have 15 answers, and I'll share the results with you. So let's continue. We had sigma. When we know this population standard deviation, then it's a sample, etc. Makes it a Pelican problem, and then we use it as that table. The alpha value pretty much is given here, so 0.05, and it's a two-tailed test because they don't specify about being more than 960. They also don't say being less than 960. They are just saying, is it 960 as we expect? And in this exercise, you will notice that there was this thing talking here before. Oh, is it not drawing? It's not drawing. There was this part saying, compared to an earlier model that provided only 750 lumens. But we don't need to consider anything for this one. Let me have a look at how were the answers. So Pelican, 7 out of 15. So almost half of you got it right. That table, 9 out of 15. Very good. What type of alpha the value of alpha? 0.05. 13 out of 15 got right. Very good job. And finally, two-tailed test got 6 votes, and it was a little bit of split here, but I understand that the 750 lumens might get in the way of getting this one right. So stop sharing so we can go ahead with the exercise. So, but let's do the steps that we usually do. Step 1, and put all the data in here. State H0 and H1. So our null hypothesis and our alternative hypothesis. We always start with the alternative hypothesis, which, remember, alternative is the one that things change. They are not equal. So, and since it's a two-tailed test, basically mu, we're testing if mu is different than 960. Since this one, it's a different, therefore the other one is equals, right? Mu is equals to 960. Notice the alpha, 0.05. Therefore, since it's a two-tailed test, we split in 2 parts. We have the X bar distribution here, and then we can do that transformation to a Z distribution. And as we've always been doing, the areas are the same, although the values might not be the same. X bar upper crit and Z upper crit. The area inside of the distribution is the same, right? So this is the mu, and because we subtract mu, here it's a 0. All right, step 1. Let's go. Step 2. Use the p-value approach to for our step 2. So decision rule, usually we're doing a reject H0 if the absolute value of Z-calc, and we have this absolute value because it's a two-sided test, so sometimes it might be a -1. So we just want to see how large it is. It's bigger than the Z grid, right? Which means if the thing, the value we have falls in here, or to the left of the lower grid value, or to the right of the upper grid value. But in this case, they are asking the p-value. So what does it change when we're trying to do using the p-value approach? Look, what we're trying to do, as you've seen in your lecture, is to see the p-value is not a little value in here anymore. It's actually the area that we have in there. And since it's a two-tailed test, we need to look, this p-value will be considered the area in both. So what we're testing is, if this guy falls in here, the little area times 2 is smaller than alpha, because alpha here it's kind of considering both areas. So this is a little bit how it works, right? The area is always positive 2. And what else do I need to say? That's about it. The alpha, since it's an error, I try to put everything in red so you can see we're talking about the same thing, both in the Z distribution and the X bar distribution, and in here, everything rejection region in red for this slide, okay? Let's continue then. Next step, we're calculating our Z-calc. And we start with the Z-calc. So, and then we go to the p-value. So basic Z-calc with our X bar minus mu divided by the standard deviation of X bar, which is standard deviation of the population standard deviation divided by the square of n. Let's replace the values there. So 954 minus 960 divided by 18.4 which is divided by the square of 20, which you find minus 1.46. So this little guy here, this sample we have gave us 954 lumens, a little bit less than what we're looking for. That's why we have a negative. And where does this Z-calc falls into? And what does it mean? Actually, I'm sorry. When it comes to p-value, this is the probability that Z is smaller than minus 1.46. So remember what I said. Think about a Z, draw a line on minus 1.46. We haven't calculated it, so it might be to the right or to the left of this part. We know it's negative, so it's to the left. P is the probability that Z is smaller than that little one, minus 1.46. So P value is the area that encompasses that thing there. Okay. In this case, I should have said P value divided by 2, because it is, I think I fixed for the next slides or something, maybe I left it past. But when we look at one side, we need to then multiply by 2 because it's a two-side test. Okay, let's go on with this one. So the probability of this little area is equals to 0.5, the whole thing, minus the probability of Z being between 0 and minus 1.6, which would be the other side of the little thing, which is equals to 0.5 minus the probability of 0, the Z being on the other side of the same area. Because this is symmetrical, right? The standard and normal distribution. Therefore, you can check both sides. This is just an extra thing for you to think about. It would be the same, but the p-value is the difference. So the little tail that we have, right? So let's look for it. we found Z equals to 1.46. Can I please have on chat? What would be the area of 1.46 for the Z value of 1.46? Amazing. Thank you so much. You were very right. 4279. And continuing that. So the thing is, this area is the part that touches the 0, as we've seen up in here. Therefore, the p-value is the difference. So it's this little 0.0721. Okay. Then this would be a little area in a certain part to the left, but we need to multiply by 2 because the p-values, it's both sides. So the p-value we find for this exercise is 0.1442. That's it. For this exercise, you see area of one tail. I try to call the attention for this one here. And that's it, how we do for the p-value. So going back, step 4, let's make a decision. Is our p-value smaller than alpha? Or is 0.1442 smaller than 0.05? As you guys can see, it's not. Therefore, we do not reject the H. This area is, let me try to represent a little bit. The addition of these two sides gives us 0.05, right? Maybe I should have kept it in red here. Since this area is larger, it means our p-value is a little bit larger. It has more area. So it means it is a little bit more to the right here or to the left in here. And we can see it because we found 0.07 for just one side. 0.07. It's larger than 0.025. So that's where it is. You know that our rejection regions is to the right or to the left here. Therefore, we're not rejecting H0. So, step conclusion. There is insufficient evidence at the 5% level of significance to suggest average light output is different from 906 lumens. All right. That's it for exercise 1. If you guys have any question, feel free to open your mic or send a message in the chat. Question 2. Polls. Let's go to the polls. I'll launch. So, an electric company indicates 18% of all households in a particular community on personal computers. A study of 80 families with school-aged children in this community found 22 of the families owned computers. Test whether the proportion of families with school-age children owning computers is higher than in the overall general community. Using alpha equals to 0.02, do the hypothesis test in 2 ways. So let's have a look. I have 2 answers up to now out of 24 of you. I think I will give you another minute. 4 answers now. So the values we're looking for are, what symbol would you give to the value 18% of all households? The other one so an electric company indicates 18% of all households in a particular community. The other one is 80 families. So where is it? A study of 80 families with school-age children is in this community found 22 families owned a computer. So the 22 families is coming from somewhere else. And I think I made, I had let me see if I fix this. I did change it a little bit. I'm looking at the slide. I have to fix the slide. It's not updated with the questions. The questions are right. So the third question is, what symbol would you give to the value 0.02? And finally, the last question is not this one, but to calculate p hat, because this one wouldn't be very correct. I have 19 answers, 20. So I'm going to end the poll in 10 seconds, maybe, for the last 5 that are missing. All right. 4, 3, 2, 1. And 20 answers. Very good. Thank you, guys. Let me share and share also the answer with you. So what symbol would you give to the value 18% of all households? This is P. This is and 10 of you got it right. This is talking about the population proportion, because it's an electric company indicates. It's not a sample, it's something that we had before, right? Very good job. 10 of you got it right. Second, what symbol would you give to the value 80 families? 80 families is the size of our sample. 17 out of 20 of you got it right. Fantastic. You guys really know what you're talking about here. Once again, 0.02 is alpha. 15 got it right. And finally, how much is p hat? It is 0.275, and 14 of you got right. This is amazing. Very good job, guys. Very good job. It seems like I didn't fix the previous slide, but I fixed this one. Apologies for that. I'll stop sharing. So what type of problem do we have? Let's go for this one. Oh, I just type of problem. Let's relaunch poll. Nice. So once again, I put the values we have in here. I think this one gives enough advice for you to choose amongst everything. I'll give, for the poll, I'll give you just 1 minute for it. I still have the same setting here, but I'm sure this time all of you will get it right, because there's a lot of advice for which one it is. What else? I would say there is a little bit of advice for this one too. And that is all I'm going to say. Another 15 seconds. I have 13 answers out of 26, 14. Another 5 seconds. I usually give just 1 minute for this one, because you've been doing the same over and over. I think by now you probably very proficient in doing it. So 17 answers, that's it. 18, I will end the poll. Amazing, good job, thank you. Share results, and look at that. This is a freaky fish problem. This is proportion. This has a p hat in there. So that's what we're working with. 7 out of 18 of you got it right. But I understand that we haven't been doing it for quite a little while, I would say. It's not the one that appears the most. We do a lot of Pelican, so okay, I understand if you didn't get it right. Z table is the one we use with the freaky fish. 14 out of 18 of you got it right. Alpha 0.02. 16 out of 18 got right. And finally, what type of test is it? A one-tailed test, upper tail. And why is that so? Why I didn't select which test it was? So tests where the proportion of families with school-age children only computer is higher than in the overall general community. The thing about higher says that, okay, this is going to be our alternative hypothesis. Therefore, our null hypothesis could be equal or lower. It could be both. All right, let me stop sharing. And let's go. So test whether the proportion, first, use the critical value of the statistic. Step 1, let's state H0 and H1. First, the alternative hypothesis. P is bigger than the 0.18 that we had there, one-tailed test. Step 2, P is smaller or equal to 0.18. It could be just P equals 2 if you wanted for the null hypothesis. But the very important is the alternative hypothesis. Putting down all the information we have, it's a one-tailed test, so the whole alpha goes to the side we have. It's here a distribution of our p hat and a distribution of z. I put the formulas in there. Now we're following each of the steps as we did before. First, decision rule, reject H0 if it's z calc, the absolute value is greater than z crit. In this case, do we need to say it's an absolute value? Probably not, because it's just to the right of z. So this value is positive. So if things are in here to the right of it, this z calc will be larger than our z crit. The crit is this line, and the z calc is what we calculate with these values. All right, so let's go. How to calculate? We have 0.02 there, therefore it's a 0.48. Let's go to our table. Can I please have the 0.48 there? 0.48, the area. Remember, now we're looking at the area. I try to use color coding for it. So when we have the area of the distribution, we're looking for the z value, z crit in this case, 2.05. Thank you, Madeline. 2.05. Excellent. Jasna, too. Thank you. Very good job. Let's keep going because I'm doing it slightly slower. Very good job. So calculate. This is our z crit, right? The line. Now calculate z calc. It's where it falls in. We're using basically the standard formula we have. Replace this little guy there. So we replace the value 0.275 minus 0.18 and get a 2.21. If you look at the Z table, you can already start guessing, oh, where does 2.21 falls in here? Is it to the right of the crit or to the left of the crit? Is it in our rejection region or is it not in our rejection region? I think you guys can get a feeling. So step 4 is making a decision. So 2.21, is it bigger than 2.05? Clearly, the answer is yes. It's in our rejection region. Therefore, we're going to reject H0. Okay. A conclusion. I think my camera might be on the way. Let me take it off. There is sufficient evidence to suggest that the population of families with children who own computers is higher than 18% at the 2% level of significance. So in this case, we're talking about we're talking about this based on the study of the school-age children in this community, right? So there is sufficient evidence which shows we reject H0 in favor of H1. We'll reject the null hypothesis in favor of the alternative hypothesis. All right? Okay, let's keep on going. But they asked us something else. Second, use the critical value of the sample proportion. And what are we talking about here? Now, instead of using the Z that we used it, they are asking, I want to use the critical value of the sample proportion, the p hat crit, this little guy here. So the only thing we're doing is to move the calculations we did up to this distribution, the p hat distribution, instead of z, right? So let's go with it. So reject H0 if p hat, wherever it falls, it's greater than p hat upper crit, which is this little guy here that we had before. So P hat upper crit, it's equals to the P that we had before. So not the P hat, but P. And we're trying to find the critical value plus Z crit times our how can I say it, sigma of a P hat, or our standard deviation for P hat, which is this formula in here. Just replacing the values, we get a 0.268, and this is the crit. This is where this red line is sitting. Okay, this is only using the red, guys. Now we're going to use the rest of the things to find what our sample concluded about it. Now, step 2, calculate P hat. P hat we already had is 0.275. Is it to the right or to the left of 0.268? Clearly, it's a higher value, so it's supposed to be to the right. Oh, I clicked here. I think could have clicked it before. We're going to reject height 0 because it falls to the right. And I would expect you guys not to be surprised by it happening right now, because we have just done it with the Z crit. Why would it change for the P hat, right? We're using the same values for P, same values for N, same value for P hat, and same value for alpha. Therefore, we shouldn't be surprised that we got exactly the same answer as we got in the first part. Okay? Let me check the chat to see if there was any question before we go to the last one. All good? Good. So let's go. We reject height 0. Rejected height 0. So let's do something more. The last question is, if the proportion of families with school-age children owning computer was actually 17%, what error, if any, had been made in part A? So first, what did we do? At this time I left the text. We reject height 0, right? So I will click once. I hope it works. This I know. Now, can I have on chat what type? Did we do any error? And if we did, what type of error was it? Can I have in chat? Because it's saying that the proportion of families was actually 17%. Which means my question is pretty much, should we have rejected height 0 or not? We did reject based on our sample, but should we have reject given the whole thing is actually 17%? And I'll follow on with this. I know it's a little bit more complicated to choose the error we're doing, but look, height 0 is true. Or I mean, it's not true, but we shouldn't say that ever. We should not reject height 0, or we should not have sufficient evidence for rejecting height 0, because look, P for height 0, P is smaller or equals 0.17, and you know the 17% is lower than, it's 0.17, which is lower than 0.18. All right. So we should not have, this is a type 1 error that we committed. We did reject height 0. Well, we should not, because height 0 is true. That's how we say here. All right. Do you guys have any question? This is the end of the second question. And finally, we go into a longer and more complicated question, which will still allow you guys to put on the symbols and everything. You were reminded of another long one that we did before. And feel free to open your mic or send something in the chat if you need. Okay, one more click, and there is the poll questions. There are the poll questions, few of them. So the executives of an adhesive manufacturing company whose product is used to attach heat shield tiles to the space shuttle are concerned about the performance of their product. So rocket science, right? Space shuttle, the rocket that goes to the space. And this is the heat shield tiles, the things that protect them when they're entering Earth again. So they find the drying time is excessive. So the things when you glue to protect the heat shield. The research and development laboratory has produced a new adhesive that the company hopes is superior to the old one. And now we're going to the information we have with the symbols. Let me just have a look at the poll. I have 7 answers already, but yeah, I'll give you another minute. So to test the new adhesive, the 25 tiles are attached using the old adhesive and 28 using the new adhesive. The mean and variance of drying times were found to be 7.244 hours and 1.6209 hours squared for the old, and 6.64 hours and 1.1275 hours squared for the new. From past experience, it's known that the drying times are normally distributed. At the 5% significance level, using the p-value approach, can we conclude that the new adhesive is superior to the old? Let me have a look. 16 people have answered out of 26. I'm giving a little bit more time for this one, maybe another 15 seconds. How does that sound? 17. All right, I'm missing just 9 answers. Pretty much, it's just 4 questions. I packed them into groups. A few of the things, 2 values. So same symbol for 2 values in 3 of our questions. And that is it, 17 answers. That's what we're getting for this one. I'll share the results. And let's go. So 25 and 28 tiles. It's the size of our samples, the samples that we're comparing. What symbol would you give to the value 7.24? These are X bar. So let me see. And 12 out of 18 of you, got it right for the first one. Second one, 10 out of 18 got right. Fantastic. It's an X bar, therefore you know that this is an S squared, right? For the second one. So standard deviation of the samples. Very good, 9 out of 18 got right. And finally, our alpha 5%, 13 out of 18 got it right. Fantastic job. I'll stop sharing so we can go to the next one. Next and final poll for today, because there will be a little bit of working for this question here. Let me do it again. Relaunch poll. There you go. You guys have the next one. So have a look here. We have more information. I can see that my X bar doesn't have the bar on top of it. Probably you guys are seeing the same. This bar should be a little bit longer, but we've done this type of exercise before, right? Let's see if you can find. In the poll, I have 2 answers up to now. I know I'm rushing a little bit. You have another 30 seconds to answer this one. And pay attention to what type of table we'll be using, depending on what answer you have for the first one. And the alpha value, pretty easy. And what type of test it is, must be the more challenging question in here, I would say. I have 12 answers, maybe another 10 seconds. 13 answers. 14, 15, fantastic. All right, that's good enough, guys. Good job. Let me share the results and let's go. Let's discuss it. This is a salmon versus trout. we're comparing. It's the difference between two samples, right? And let's go. I had just 3 of you got right. I'm not surprised. It's challenging. And it's the first time that I do this poll with an option for salmon versus trout. And the advice here is that we're comparing 2 samples. Both are samples. We're not comparing population with sample. It's 2 samples. So look at this table and remember that we've done it before. 2 tutorials ago in tutorial 8, we had, I think was Taringa and West End here in Brisbane. And all right, but that's okay. 3 of you, now you know when it's like that, when it's paired, like the values are paired like that, we're talking about salmon versus trout or population mean difference, right? Because of that, it's the T table. Fantastic. 11 out of 15 of you got it right. It's a 0.05 for our level of significance. How many got it right? 13 out of 15. Great. And for this one, it was tricky. And I was just adjusting this these slides before our tutorial started, because it could be an upper tail test or it could be a lower tail test. It depends on the order of things that you do. So something to pay a lot of attention, and we're going to work through it right now. I'll stop sharing and let's go to the results. I put it in here. So step 1, state H0 and H1. Let's have a look at them. First, I'm saying that, hey, mu of the old, there is a little O here, minus mu of the new is bigger than 0. Why are we saying that? So let's try to interpret a little bit. So we're asking, can we conclude that the new adhesive is superior to the old? Being superior means drying faster in a shorter period of time. So this number here, this number should be smaller than this one. Since this should be smaller than this one, therefore this minus this should be bigger than 0. So that's the interpretation, okay? Let me click once again. If this is bigger, you know that for the alternative hypothesis, you know that the null hypothesis will be the mu of the old one minus it's smaller or equals to 0. But we could have done everything to the other side. We could have said, put the new first, and then subtract the old. And some people might think, okay, this is actually the intuitive way, given the way it is written. You subtract the new from the old from the new, whatever. It depends on your rationale. Then it would be, so the new, as it should be smaller, this minus this one should be a negative number, because this is smaller, right? So the bigger number has a negative, and this, therefore, this subtraction should be smaller, and then the null hypothesis. We have both options. In our case, we're going to choose to continue with bigger than. Therefore, we're only looking at this side of our rejection regions. It's a one-tail test, so just one side. And that's what changes. If we were using this other one, we will be looking at the negative side. And we will be discussing, for the t value, we would be discussing negative values. Okay? Let's go then. Look how some different things are there. The center is the difference. So it will be mu of the old one and minus mu of the new one. Okay, this is the rejection region. So following the same system that we have here. And since our alternative, it's saying greater than, therefore we're looking at the right side here, the rejection region. And because it's just one tail test, it's the whole value of alpha, 0.05 is there, right? So the whole setup of the things here. As you can see from this slide, things won't be as simple as the previous ones. It's a comparison of means, so we have to calculate a little bit more, a few more things. So let's go to step 2. They want us to use the p-value approach. So we're discussing p-value is area. We're talking about area. There will be the alpha that we already know, 0.05. And we want to know if the p-value, and for this case, it's a one-side test. We're not multiplying p-value by 2. We're just looking the p-value in here. If it's smaller, therefore the little area falls in here. If it's greater, the little area will cover a little bit more. So we do not reject in here, and we do reject if it's a little guy in here. Okay? As we've always been using, at least as we've been using during hypothesis tests, last tutorial and this tutorial, right? Still same rules, just different equations. So let's go. Step 3, calculate T-calc. We know alpha. Now we're calculating T-calc. But is this the formula we're going to use? We're not looking really at the x-bar, but a difference of 2 x-bars. So what we are looking are these guys in here, in the slide. What we have, let me make it a little bit smaller here with the camera. What we have, if you rearrange the equations, T is equals to our, this is mu, is here, right? So rearranging, you got T-calc is equals to the difference between the sample means minus the difference between mu, the population means, divided by this standard deviation of the difference of the sample means. Standard deviation of the difference of the x-bars, if you will. And these are the formulas. So let's go. Let's try to calculate it. First, T-calc, we know T-calc, but to calculate this standard deviation, we need to use the formula in here. And to calculate this one, we need the pooled variance, which is this other formula. So big thing, big calculation. One thing you notice, no matter which of the values you chose, or which of the sides of rejection regions you chose, we're adding things for the x, s of x bar 1 minus x bar 2. So these two guys would still give you the same value. What would change would be the value in here. This is the only one that changes. Okay, because as you can see, our x bar has different values. So this minus this one is a positive number. I have the values. Sorry, I have the values changed here. Apologize for that. Let me, before I continue with the explanation, I might have to fix. I fixed for the next ones, but I didn't go all the way back. Okay, this is probably all I have to fix. Oh. No. I did fix. Sorry for that. Look. Okay, where did I stop fixing it? This is right. This is wrong. Okay. Now it looks better. Now it looks like what we want. Whatever. That is good enough. Okay, now it looks a little bit better. So apologies for fixing this one. We can continue. There are our values. So subtracting from where I was. X bar, if you do this one minus this one, you get a positive value. But if you go the other way, this one minus this one, you get a negative value. But for the rest of it, for S of X bar, standard deviation of the X bars, the difference of the X bars, you still get the same value no matter what you chose. Let's go. So replacing the values for our pole variance, you have here 25, 28, and also the standard deviations. And this is what we get, 1.35. Important thing to remember, try to use, if you're doing it on a calculator, try to use the calculator memory, because you would need to use a lot of decimal numbers here, decimal places, because if you just use like 2, 3, you might get a different answer than what they're expecting in your CML or LBRT. Okay, try to use a lot of them. Then replacing it in here and 25, 28, we get this for our standard deviation of the difference of the X bars. And finally, our T-calc, we have it here. And now our T-calc is 1.88. Right? So let's continue. We found our T-calc. Now let's have a look at our T-crit. So our T-crit is this one here. And I wanted to call your attention. You will see in the formulas that when we calculate a confidence interval, there is an alpha divided by 2, because we look at both ways when we do a confidence interval. We do a lower bound and a higher bound, or I think the other way around. But in this case, it's a one-tailed test. So we're looking at alpha. It's the whole 0.05. Look at it here. And then the second parameter we have is N1 plus N2 minus 2, which is 51. So 25 plus 28, 53 minus 2, 51. And let's go. I'll ask your help. And look, I'm asking 2 things here. Can you please give me in the chat? I'm asking you guys to look for our crit value, the T 0.05, 51. But I'm also asking you to look for this 1.88 value, which is our T-calc, the value we found for our T at 51 degrees of freedom. The same way, both of them are 51 degrees of freedom, but one is our T-calc and the other one is our one is our T-crit and the other one's our T-calc. Can you guys please just send me the first one? The second one, I'll tell you, you probably won't find, but it's between 2 values. Not advice there. Perfect, beautiful, excellent. Jesna, Shahan, excellent. Xingling, thank you for that. For the 1.88, Keanu measuring, amazing. For the 1.88, at 51 degrees of freedom, have a look at what we find. It is between T.0.5 and T.025. It falls in between this region. So we can say it's in between these 2 values, pretty much. Yeah, that's what I wanted to say. And it's more important, this conclusion, than finding the other one for our exercise. So let's go. So we found this value for our T-crit, 1.675. I just put this guy there. But our p-value, although we didn't find an exact area for it, we know that the area is smaller than 0.05 and it's greater than 0.025, right? Where does it put our p-value in this little area? Since it's smaller than 0.05, therefore it should be a little bit to the right here. It's probably not too much to the right because it's greater than 0.025, right? So it would be somewhere close to the line, but to the right, which is a rejection region. being a rejection region, guess what's going to happen? P-value smaller than alpha, rejected here. We have the answer for this one in here because alpha is equal to 0.05. So look how interesting, and I'll go back to what we were doing, and I'll scroll it up a little bit. But look where we noticed that it was smaller. Can you see that it's decreasing here? There was the T at 10%, then at 5%, and then at 2.5%. And we realized it was after the 5% and before the 25. Therefore, that's why we're rejecting. It's a tricky thing, something that to practice a little bit until you get used to. But it's a important concept to understand why we are rejecting in this situation. Probably your CML will be asking it, and possibly the LBRT, who knows? But this is a type of exercise that requires a lot of equations to be used. So you guys need to be comfortable with using them. All right. I have nothing in the chat. So conclusion, there is sufficient evidence at the 5% level of significance to suggest that the new adhesive is superior to the old one. So the drying time is better than the old one. So the space shuttle might use the new one so they can attach quicker. That's the idea. All right. So let's go. Question part B. What assumptions underlie your analysis? So remember in our slides, there is this slide here. It's either lecture 8, or 7, either 7 or 8. You will have this one, slide 24. These are the assumptions we make when we're doing this, comparing two samples. So comparing the difference between means, right? Assumption 1, variables, mu for the old one and mu for the new one, the drying times, the mean drying times are normally distributed. We're assuming that's what how it works. As another assumption, the samples are randomly and independently taken. So this is an assumption that we need because we can't just go and pick the same tiles from the same batch. There needs to be some randomness there, and usually all the or most of the research done, they need to have a random sampling. For example, I'm testing a type of drug. You don't want to get everybody with the same age or from the same gender or from something else, right? Same height, I don't know, something like that. So it needs to be randomly and represent the population. Next, I'm just associating here with which one we're talking about. Finally, the variances of the samples drying times are equal. This is an assumption because we're doing a pooled variance with it. So we are trying to get in kind of an weighted average of the variances. If they're not really equal, if they're extremely different, then our analysis is not really good. That's what it means. All right. And these are the assumptions that we have. You can find it on this slide. Please try to make, put away, I know there are many slides, but select some key slides with the formulas you need or some theory that might be important, like the assumptions, for example. Have a look at the ones I've been using in the tutorials to make sure you have some things at hand. So when you go to do LBRT, which has just 90 minutes, it's a limited amount of time. So you have everything easy to access. All right. Another advice there for LBRT. Next, question C. Estimate with 99% confidence the average drying time of the new adhesive. And I'm calling the attention about this 99%. Look, we were using 5% before. So now that it's 99, don't forget to change your alpha to 1%, 0.01, because the 99% confidence is the 1% significance, level of significance. All right, let's go. Look, it's not a salmon versus trout anymore. This is a confidence interval, and it's just talking about the new adhesive. There aren't two samples anymore for this item. It's just one sample. So I changed here to our friend Shag, and I brought back the slide, I would say, from the lecture that we have, the formula. So we're looking at the X bar plus or minus the T, and look how interesting. The T before in A and kind of in B, we're using the alpha instead of alpha divided by 2. This is because we were doing a hypothesis test, and we wanted to look at a one-sided tail. It was one-side tail, or just the upper value, or if you chose things in a different order, the lower value. That's why we use the whole alpha. But back in the confidence interval, we're again looking at two things. We will calculate the mean and the upper and lower bounds. For the confidence intervals, it's upper and lower bounds, right? So plus and minus, and alpha is divided by 2. Therefore, this is why the T we're looking for is 0.005. And the 27 is pretty much the 28 we have here, minus 1, 27, which are our degrees of freedom. All right, let's go to the table. Can I please have on chat the T 0.005 and 27 degrees of freedom? Nice. Amazing job. Very good. Very good. Thank you, Kenny and Madeline. So what we have here, you look at the 27 degrees of freedom, then you look at the 0.05, and then you get 2.771. Excellent. All right. So we have our T value, 2.771. So to calculate, just replace values. One tricky thing, important thing. Oh, then I changed something. Look, the formula is using S, standard deviation, but the values we have are S squared variance. So this can be tricky. And you might have it in your CML or LBRT. They give you a value of variance and then ask you to calculate the confidence interval. Pay attention. You need to square that value, because the confidence interval and the standard deviations in general, they're calculated on top of your standard deviation, which is the square of your variance here, right? So let's go. We find this value. I see a little thing here, but basically the values you will find is 6.8084, smaller than mu of the mean, is smaller than 7.196. So we can conclude that it is estimated with 99% confidence that average drying times for the new adhesive are between 6.084 and 7.196 hours. So the time for the new. All right, let me check the chat before we go to our last question. Excellent, no questions there. Feel free to send any question if you have. And back to our salmon versus trout, because now we're talking about two products again. Estimate with 95% confidence the difference between the mean drying times of the two products. The difference between the mean of the two products. Is it the same as we did in A? So first, 95% goes back to what we did here, 5% level of significance, so 95% of confidence. But now it's back to do our confidence interval. Sorry, we're not doing a confidence interval, we're estimating the mean with mean drying times. Sorry, the average of the difference between the means we're calculating. We are not asking if it's higher or lower, or if it's better or worse. We're calculating the mean difference. So now it's a two-tail. Again, now it's back to what we did before. It's not even a hypothesis test anymore. Like in C, what we're doing in D, again, it's the salmon versus trout, but it's related to what we did in tutorial 8. Okay, not hypothesis test anymore. We're not testing if it's higher or smaller. It's just the difference of two means, which we did during confidence interval, and we're going to use the same things that we always use. So let's go. Confidence interval, as you can see here, mu1 minus mu2. I chose to use just to have old minus new, just to have an indication of what we're talking about. And the rest of the formula, it's exactly the same. And the good thing is that we've calculated a few of these guys already. So I'm bringing for a question A, the difference between x bar 1 and x bar 2, which is nothing else other than this minus this, right? 0.604. And our standard deviation of the difference of the sample means, we calculated 0.3208, and feel free to add more decimal places there. The more the merrier in this situation. The only thing I can't take from that is the t of alpha divided by 2, because before we were using alpha only. We were looking at a one-side tail test. So we will have to calculate it again. So let's do it. Alpha divided by 2 will be 0.025. And the degrees of freedom is the addition of both, 53 minus 2, 51. Let's go. Probably the last time you're looking at the t table for this tutorial. Don't be too happy. You might be looking again next week. Fantastic. Amazing, guys. Good job, Jasmine. Can you? Just giving Madeline, thank you. Just give a little bit of time to see if other people would indicate something. So look, 51 degrees of freedom, and the t we're looking for 0.25, so 2.008. Excellent, good job, guys. So this is what we found. Replacing it in the formula brings us to 0.605 plus or minus the 2.008 times 0.3208 values. Also using the values from the previous exercise, which gives us from minus 0.048, smaller than the difference. And remember, when we're talking about it's mu, it's the population mean again. So the population mean for the old tiles minus the population mean for the new tiles is smaller than 1.248. So let's write a conclusion for it. It is estimated with 95% level of confidence that old drying times are between 1.248 hours longer and 0.04 hours shorter than the new adhesive times. Look how interesting. Minus on one side and plus on the other side. You wouldn't be surprised, given we're taking a difference, because it's a difference, and this will be used a lot in the future in another course, the one that comes after this. Since we have left a negative on one side, and looking at US negative on one side and positive on the other side, that means we probably did not reject H0. Our t statistic was too small to reject. So yeah, it's not too relevant for this one, but it's important to know. So that's pretty much what happened. Before I can't remember, because we were using alpha, so it was a little bit different, but all right. All right. That's not what they're asking. This is not a hypothesis testing. So pretty much forget what I just said, I would say, maybe. But that's it. This was the last item of the last exercise for tutorial 10. This week, at the end of this tutorial, you should be able to carry out a 1 and 2 tail hypothesis tests using the p-value method. Carry out 1 and 2 tail hypothesis tests for the population proportions, our friend trickfish. And carry out hypothesis tests for the difference between two means using the pooled variance method. Thank you so much, guys, for watching this one, and I'll see you next week.